Okay, so I got a question for homework problem number 2. This is from the handout, from the homework sheet handout. And there's two parts to this question. The first one is calculate the minimum uncertainty in momentum. Calculate the minimum uncertainty in momentum of a helium atom. And the second one is calculate the minimum uncertainty in speed. Okay, so this is something that, let's see, let's just change this around a little bit. It seems crooked on my table. Okay, so, alright, first things first. Let me get a bit of paper underneath here. First things first, calculate the minimum uncertainty and momentum. Alright, so as you know, when I first see stuff like this, my mind sort of goes blank. And I say, alright, minimum uncertainty, we're surely talking about the Heisenberg uncertainty principle. Momentum, alright, I'm starting to get oriented to this. First thing I think of is delta x, delta p is greater than or equal to h bar over 2. Right? That's the Heisenberg uncertainty principle. Alright, so calculate the minimum uncertainty in momentum of a helium atom that is known to be within 2 nanometers of a certain point on the line. We don't know which helium atom this is. Is this helium-3 or helium-4? So I look here in the back of my book. Okay, can you see that? It's maybe out of focus. Look here, sorry about the noise there. Look here at this in the back of the book, and it says helium-3 is a percent abundance of 0.00013, so it's probably helium-4. Then look at helium-4, and that says 100%. Alright, so basically in nature, all of helium is helium-4. So that would not be necessary for me to worry about whether that was helium-3 or helium-4. And by the way, I see that it's 4.0026 nanometers, or AMU. So a helium atom, I'm going to say helium-4, is equal to 4.000, is that 000? No, just 0026 AMU. I'm going to calculate, I'm going to change this to kilograms right away before I do anything else, because I know I'm always going to need things in SI units. So I go here to the front of the book and find that 1 AMU. Can you read that? Is that off camera? That 1 AMU is 1.661 times 10 to the negative 27 kilograms. Alright, so this is 1.661 times 10 to the negative 27 kilograms per AMU. And I'll calculate that in a second. Before I do, though, let me point out that there are 2 sig figs here. Okay, is my camera crooked already? Wow, how'd that happen? 2 sig figs here. And so, and I've got 1, 2, 3, 4, 5 sig figs here. So clearly this is going to be my limiter. I put 4 here just because. Right? In the end, it's not going to matter. So 4.0026 enter 1.661 times 10 to the negative 27 times. This comes to be 6.648. 6.648 times 10 to the negative 27 kilograms. Okay, and so I'm taking care of this now. Is known to be within 2 nanometers. I'm almost done interpreting this question. Within 2 nanometers on a line. So let's suppose this is the line we're talking about, and this is where the helium, this is the certain point, right? That's the certain. It's within, the helium atom is somewhere within 2 nanometers of that certain point. So that means if this is 2 nanometers away, it's either in here, in that range, or this range, 2 nanometers. This is minus 2 nanometers, or 2 nanometers to the left, 2 nanometers to the right, and of course this told is 4 nanometers. So delta x is equal to 4 nanometers. Okay, is that off camera? This is my certain point. There's 2 nanometers to the right, 2 nanometers to the left, and that is what within 2.0 nanometers of a certain point means. That's what that means. Okay, so delta x is 4 nanometers. Alright, now I think I'm ready to interpret this question, or rather to do it. Okay, we spent some time interpreting it. So delta x, delta p is equal to h bar over 2. What is the minimum uncertainty in momentum? And so I'm going to say this: delta x, delta p is greater than or equal to h bar over 2. Delta P then, which is my minimum uncertainty in momentum, is equal to delta x h over 2 delta x. And I already have this. Where am I here? Yeah. This is the same thing as h bar, which is, we'll look that up in a second. H bar 2 times 4.0 nanometers. And that's my answer. So let's look up h bar. I never remember h bar, so I'm going to say it's equal to h over 2 pi. 6.626 times 10 to the negative 34 joule seconds over 2 pi. I'll calculate that out. Can you see what I'm doing here? Yeah. The front of your exam is just kind of 6.626. Oops, just a second here. .626 times 10 to the negative 34. Enter 2 divided by pi divided by. This comes out to be 1.0546 times 10 to the negative 34 joule seconds. Okay. I'm a little worried I'm getting off camera here. 1.055 times 10 to the negative 34 joule seconds over 2 and 4.0 times 10 to the negative 9 meters. So this comes out to be 2 divided by 4 minus 9 divided by 1.3182 times 10 to the negative 26. And this is momentum, so it's kilograms meters per second. And that is the minimum uncertainty. That's as precise as we can get about the momentum. Okay, so that's part 1. Part 2 then, I'm a little afraid I'm getting off camera here. I'm sort of losing track of where I am. Getting my tape up. So we know that delta P is equal to m delta V. What's the minimum uncertainty in the speed, right? That's what we're worried about here. So we already have delta P, and we know the mass. So delta V is equal to delta P over m, which is equal to 1.3182 times 10 to the negative 26 kilograms, or meters per second, over, and we calculated the mass of this particle a few minutes ago, 6.648 times 10 to the negative 27 kilograms. 6.648 times 10 to the negative 27 divided by, wow, 1.983 meters per second. Wow, that's amazing. That's our minimum uncertainty in the velocity. Okay? Alright, hope that's helpful. Problem you may see tomorrow on the exam, right?